Okay.
But this is the right transition. So this is about melting and freezing procedures in the test facility. It will be a bit shorter than the first one, and yeah, just as an introduction, in case someone joined later. As I said this morning, we have the TESIS facility, stands for Test Facility for Thermal Energy Storage and Molten Salts, and it's made out of two separate plants, a single tank storage test facility and the component test facility. Already introduced the second part, the storage facility, where we can do the testing of a single tank storage concept. And here's also a slide showing the working principle of the component test section. So the working principle is quite similar to the other one. We have also two reservoir tanks for hot and cold molten salt. The difference here is that we have a mixer attached, so we can mix both streams, and like basically like you have at home, you have hot and cold water, and then you have a mixer where you can mix any desired temperatures, and this allows us also to quickly change the inlet temperature in the component test section. And so here's some pictures of molten salt. This was when we drained a smaller oven. You can see on the left picture, this is where we started draining the salt from the oven in a pan. And the right picture is then, I don't know, maybe 1 or 2 days later when the salt was solidified. And here's a very salient feature of molten salt when you compare it to water. It has an opposite behavior when it is freezing. So you can see it here on the magnification on the right, that it is actually shrinking during the solidification process. You can also see it here on this picture that there's a gap forming when this happens. And when water is freezing, then you have it the other way around. It's expanding when it's freezing. So this is something you have to bear in mind. And if you melt molten salt, and particularly inside a plant, then the melting process is the critical process. And if you had water, then it would be the freezing process. Now, why do we have different freezing and thawing procedures in our plant? There are several reasons for this to happen. Of course, the first one would be the initial melting process when you commission such a plant. And the next one would be purposely testing the melting and freezing process. But then there's also several occasions where you would have unwanted freezing and melting. One thing where it happens is when it's freezing in the salt lines due to poor trace heating. Then another reason might be caused by dripping salt from leaking valves. And the last reason we often see this is after shut-off, so that we have some sort of afterflow. And then you switch off the trace heating and there's still some salt coming out from somewhere and slowly flowing into your piping, and then it can agglomerate at some positions and you have clogging. Yeah, here's some pictures from the initial melting of the molten salt. So this is I mean, it looked quite spectacular, but it's quite straightforward. So typically the salt comes in some larger packing units. Here it was delivered on some pallets, and then we had a company with a like a big vacuum cleaner, which was sucking in the salt and then pumping it in a granular form into the storage tanks. So this is what you see here. We attached just a hose to the storage to the reservoir tanks, and it was blown into the tanks. And from there, we were then able to melt the salt inside the tanks just with the trace heating. Then that was within the first project we had in the ThysisCom facility, where we did a dedicated test procedure for a targeted freezing test. And what we had was a pipe section, and the pipe section had 4 segments where we had 4 independent trace heating lines, basically, and also multiple thermocouples inserted into the salt line to measure the temperatures inside. You can see that in the left picture. And what we also had here were some high temperature strain gates, which are specifically designed for high temperature applications. So they are quite costly. So typical strain gates cost around 50, 100 euros maybe, but these are some high temperature versions. They cost around 1,000 euros each, and then you still need someone to apply them to the piping, which is also something.
What's the temperature range they are good for?
You can go more than 560 degrees.
Okay, good to know.
Yeah. So basically, it was the colleagues from Solar Research, but we still have some information on suppliers and everything if you need to.
Okay, who was it?
Tobias Hirsch.
Ah, echt?
And yeah, okay. I think Matthias Wittmann was also involved.
Yeah, okay.
Yeah, so we had these in actual direction and in radial direction, and then we did some testing, and the initial test was sequential melting. So basically you can see that it's a bit inclined. There was a shut-off valve, so it was filled with salt, and then we switched off everything and let it freeze. And then after that, the salt was sequentially melted again. So we started with the first segment, then with the second, the third, and fourth. And on the right, on this graph, you can see the temperatures measured along the distance of this pipe, and there was just the increase of the temperature, but nothing really went wrong. We didn't see any it didn't find any measurement value from the strain gates anymore, but at least not in the report we got this from. But there was no notable strain inside the pipe, so everything went smoothly. Nothing really happened. But it is also clear that it is quite unproblematic, because if you start with the first segment, then as the salt is melting, it has some room just to leave the pipe and to enter spaces where it has room to expand. And the next experiment was then starting with the second segment. So you basically have a frozen first segment, then you melt the second segment, and the third and the fourth segment was also still frozen. And now the salt didn't have any room for the expansion process. And as you can see, it forcefully pushed the salt aside. And what was happening here is we destroyed the thermocouples. So the force was so high that it was just cutting away the thermocouples, which were sticking inside the frozen segments. There's a picture of the thermocouple after it was just cut off. And also the strain gates were damaged because the pipe itself was expanding so much that they even destroyed the drain gates. And what was done afterwards was just measuring the diameter of the pipe with an ordinary like a micrometer screw, and you could see that there was a clearly visible deformation of the piping due to the smelting process inside the pipes. Yeah, so this is something, yeah, if someone operates a plant, what is definitely necessary to avoid, that in case there's a freezing, one has to be very careful not to melt only partial sections, where sections in the neighboring vicinity where you might have the situation that the salt has no room for expansion. Yeah, then we have sometimes unwanted freezing due to trace heating. So trace heating in these salt systems is always a bit difficult task because you're limited from two, you have basically two boundaries for your temperature range. So you have an upper limit in terms of the decomposition temperature of the salt, and you also have a lower limit in terms of the freezing point of the salt. So in this case, for the solar salt, for example, you still have 270 Kelvin of a temperature spread. But this is if you say, okay, I have the spread of 270 Kelvin, then if you add half of it to the lower temperature, then you end up with, for example, 425 degrees Celsius as an optimal set point temperature for the trace heating, that you are still as far away from the freezing point as well as the, or at least the lower operation temperature of the plant in this case, and also away from the highest allowed temperature, so the decomposition temperature. So, and this sounds quite far away from these boundaries, but in practice, it can be not that well defined, because in practice there's always some locations where you might have less space in the piping process, and then there was too much insulation added for some reasons, or everything was just put into a box and you have too much insulation, and then you can easily exceed these 135 Kelvin, and you can easily reach temperatures way more than 600 degrees. And also, if you go in the other directions, also depending on where you measure the temperature for your trace heating and how long the trace heating line is, you can also have situations where you have increased heat losses due to some clamping or any other sort of components or measurement devices which cause higher heat losses. And then you can also fall below the minimum temperature, and you have some freezing, particularly if you have also regions in your plant where you have some stagnant flow. So if you think of the store facility with this siphon, during the operation, you sometimes have the salt just resting in the line, and in case you have then too much heat losses at some point, you might have some freezing there. Then another thing which can happen is unwanted freezing due to salt leaks. This is also happening if there are some cold spots, and we have seen that sometimes. I mean, we cannot look into the plant, so we cannot only assume what's going on there. But apparently, it can happen that, for example, some salt is coming through a valve. They are not typically 100% tight. And then you have the dripping, and if this continues over hours, then you might have some salt slowly dripping somewhere in the pipe, and if there's a cold spot, then it starts agglomerating and can form like a clog. And then typically when you switch on the plant, you realize, okay, there's a clogging, and you can like repeatedly switch on off pumps, and then at some point you realize, okay, now it has been melted, and then suddenly it's released. So it's typically smaller sections where you have some freezing. But we also very often see when we cut open some pipes, for example, after finishing some project, that there's very often some salt remaining in the salt lines. But as I said, it's typically easy to tackle. And finally, also in the storage facility, so this is a picture on the top where after we emptied the baskets, after we took out the packed bed, before we put in these brick materials. And this was the lowest basket, so we didn't see this in the uppermost basket, but in the lowest one. So there was also like a company coming, sucking out the packed bed material of the baskets, but we had at the bottom some areas where it was still sticking together or glued together with frozen molten salt. And this can also happen if even if you keep the plant, if you drain it and keep it hot for a couple of days, or yeah, I mean, it definitely happens when you keep it only for hours. So you have to keep it at least for a couple of days in a hot state to make sure that all of the salt has drained. Do not. This was also something we saw in the bottom of the tank. That was after the first operation. There was also some rainwater coming in because the tank was open for some while. But there was also some salt clogging in the bottom. So that's all we have about the salt freezing.
Yeah, thank you, Christian. Once more, we are asking for questions.
Yeah, please.
So we're saying or setting the meaning that you set the set point at 425 degrees.
Yeah.
That means as soon as you are dropping below 425 degrees in the plant, the heat temperature is on, or when you
No,
on the heat tracing.
No. It's not like that. So the heat tracing itself is like controlled by a PI controller, and that is following very closely the set point temperature. That's not the issue. But if you have a line going for 10 or 15 meters, having a lot of fans and valves in there, then you typically have only one point where you measure the temperature, and you have all kinds of temperature there. I mean, that makes it difficult. So it's always advisable to really think of how to control your trace heating and to break it down into sections which make sense for better control. And then it's also something from the control system. So, I mean, the trace heating wouldn't cause any error if it falls. It would cause an error if it falls below the 290, which is not going to happen because it's heating always. But it's also a safety issue. So we have a safety system which is making sure that we have no exceeding of 600 degrees due to the formation of nitrous oxides. And yeah, and then even if the trace heating thinks it's at 425 degrees, and at some point, because there's too much insulation, you can reach too high temperatures, and if you happen to have a safety thermocouple there, then it can also cause problems. I mean, obviously you don't want to have 600 degrees in your plant anyway, but it can also interact then with safety thermocouples you have there.
More questions? More discussion? Thank you again, Christian. Valeria? What's the next?
Can we take a group picture now for the online participants?
Oh, yeah. Of course.
Okay, so if you want to switch on cameras, please.
We see this session.
And can you close your presentation, Eckhart, please? Thank you.
But there are also other complications, but I mentioned once.
Not too many pictures on.
It's not so
missing.
Okay, one more. And it's done. Thank you.
Thank you, Dominic. So I continue sharing, right? Many icons on the screen. Let's use. Valeria, please. Introduce yourself.
Okay, I'm Valeria Russo. I come from the NL and I work in solar production until 2004. Today I'm going to talk about the salt melting procedure and melting and freezing test in the NL facilities. Okay. Okay, let's start with the startup and shutdown procedure on the PCS facility. The PCS is a facility realized in Carpaccio Reserve Center, and it is realized in the 2000, and it's composed by a solar collector loop of 100 meters long. This collector is connected to a tank, a storage tank, an electric heater, and an heat exchanger. This facilities was realized with the aim of testing the principal components for the CSP plant, such as tube receiver, flexible hose, valves, and all the instrumentation used on this type of plant. And moreover, the aim of this facility is also to optimize the managed procedure for the CSP plant, and also to test to make some tests on the compatibility between the materials. Okay, now we talk only about the startup and the shutdown of this plant. As we know, the transfer fluid that flow inside the plant is the molten salt, the binary mixture, the salt salt, and the freezing temperature of this mixture is 220 degrees. So all the components of the plant have to be kept at the value temperature higher than the freezing temperature. And we have two different systems to heat this component. The pipelines are heated by electrical cable, placed in contact with them. Instead, the other components like the electric boiler, the air salt exchange, and in particular the receiver, are heated by the Joule effect. So they are connected to a dedicated power supply that deliver the necessary current in order to raise the temperature above the freezing temperature of the salt. Okay. The condition for the beginning of the plant filling procedure is that all the plant components that come in direct contact with the salt must be at a temperature above of the solidification value. And for what concerns the component heated by the electrical tracing, we have here we can see a screenshot of the control system that we have in our control room, where we can see different tracing block. We call them tracing block, like this one. All this block is consisting of one or more cable, heating cable, and one or more skin thermocouple positioned in contact with the pipes in order to control the temperature of the pipe during the heating. Here is the zoom on a single tracing block, and each tracing block consists of an on-off type control system. For each one, the system evaluates the temperature, present on the pipe, and based on the setup set by the operator, this value, control the heating cable, so turn on or turn it off with any services of about 5 degrees centigrade. Instead, for what concerns the component heated by the Joule effect, so the electric boiler, the air salt exchanger, and the receiver in particular, these components are connected to a dedicated power supplies that deliver the necessary current in order to raise the temperature. The temperature is regulated by a PID controller that has a thermocouple placed in the critical points of each component. For example, for the receiver tube, the thermocouple are placed on the expansion joints. Before starting the pump, so starting the filling of the plant of the solar field, the operator have to check all the temperature of all the tracing block and of all the power supply units. Here we can see a trend of the temperature for the tracing block. All the minimum temperature of all the block are set between the 250 degrees and 300 degrees. This range of temperature depending on the mass and geometry of the pipes. We can see that in this case the return pipeline, this one, okay, is a temperature below the 240 degrees that we consider a safe temperature. And this is due to a non-perfect contact between the thermocouple and the pipeline. But this temperature doesn't affect the filling of the plant. In this test, we can see, for example, that around 7:45 in the morning, we have increased the temperature of 2 blocks. These 2 blocks are the first section, are related to the first section that will be flooded by the salt, and these 2 sections have a particular conformation with many curves, so it's better to hide the temperature above the 240 degrees because it is possible they are not be completely empty, and it could be some obstruction inside this pipe. Here instead there is the trend of the component heated by the Joule effect. So also in this case, all the temperature are set between 290 degrees and 330 degrees. Only the temperature of the receiver tube, the second part of the line of receiver tube is about is equal to 240 degrees. And also in this case, it is due to a non-perfect contact between the thermocouple and the piping. Here we can see instead the trend of the temperature along the receiver. Also in this year, we can see that all the temperature are set above the 240 degrees. When all this temperature, so the temperature of the tracing, the temperature of the component heated by Joule effect, and the temperature of the receiver in particular, are above the freezing temperature, at this moment it is possible to start up the filling process. Here is the procedure that we do everything that we have to perform some tests on the field. So the first things that we have to do is to turn on the cooling water circulation pump. Then we have to open the compressed air in order to move the pneumatic valves. Then the operator have to pressurize with air all the circuit in order to verify that it's empty of salt. And finally, we have to do a test of the movement of the solar collector. When all this test is okay, we can start the pump, the salt pump circulation. In this at this moment, the pump so forces the flow into the circuit, first filling the piping, the receiver, and then the return line. The operators can be sure that the circuit will be completely full only once the fluid is back inside the storage tank. All this process takes more or less 15-20 minutes. Here we can see a typical trend of the salt temperature during the filling process along the receiver. Every day in our plant, because the plant is quite small and is not designed, it is not designed for work 24 hours every day. So when we stop for the experimental test, we drain the salt. This operation normally we do every day. The PCS is designed to have a slope of 5 per thousand toward the storage tank. So all the molten salt inside the circuit can return in the storage tank. Before proceeding to stop the pump, we have to position the solar collector in the most suitable configuration in order to facilitate the emptying process. In this case, in our plant, we position the collector facing the geographic node, and the axis of the paraboloids are horizontal to the ground. Once the mirror are positioned in this way, we can stop the solar the circulation pump, and so the salt begin to flow in the storage tank. In order to accelerate and facilitate this process, we open also a vacuum breaker valve that can connect the storage tank with the expansion tank. The operator can monitor all this process, observing the temperature trend along the circuit and also the level of salt inside the storage tank. All this process take more or less 20 minutes. Here is a typical trend of the temperature into the piping during the draining phase. We can see that the inlet and outlet temperature of the collector initially decrease, then increase again, and this phenomenon is due to the fact that the heat tracing is still on. The operator can be sure that the draining phase is finished when the salt level in the tank is steady, is not change during the time. Okay, now as I show you another type of test that we have to investigate. We investigate the melting and the freezing inside the receiver. These tests are performed on a particular test bench that we realized inside our lab. And this test bench is it consists of a two receiver tube connected by a collar welding together this tube. At the end of these two receivers are positioned two curves, and there are two pipes in order to load and unload the salt inside the receiver. Because of the receiver have a glass envelope, it is impossible to install the heating tracing on the receiver. So we have used an impedance system to heat the system. And also with this system of heating, we are sure that the heating inside the tube is uniform. Here is presented the position of the thermocouple that we have installed on this test bench. We have installed 26 thermocouple, of which 18 inside the fluid. As we can see, for example, we have we have two thermocouple immersed at the inlet and outlet of the Q receiver. Then we have another two thermocouples positioned in correspondence with the terminal of the electric heating system. And then we have four thermocouple positioned in a radial pattern in the joint between the two pipes, so in this section. And moreover, we have also another four thermocouple positioned along the vertical diameter in the central section of the two receiver. So four here, another four here. And then we have also six thermocouple positioned on the external surface of the glass envelope. We have used a 10 kilowatt power supply with a variable voltage from 0 to 10 volt, and all the system is controlled and adjusts automatically the voltage supplied through a software developed in LabVIEW. Here we can see the trend of the required magnitude during the test. The main objective of this activity is the evaluation of the time range necessary for the complete solidification of melting of the mixture, the analysis of the receiver behavior during abnormal operating condition, and principally in case of blocking of molten salt circulation, so in emergency condition, and also another objective is the definition of the operating procedure in order to prevent damage caused by natural expansion of the salt volume during the phase change. For what concerns the test condition, in order for the solidification test, we start from a constant temperature equal to 270 degrees. You have chosen this value because we want to simulate an emergency condition in a real plant that in night circulation. And in an emergency situation, the pump is blocked, so the salt can flow inside the receiver. And in this way, we want to simulate the worst cases that can occur during the plant operating. Instead, for what concerns the melting test, we started from the ambient temperature until the completed phase change occurs. This test, we can say that this evaluation are very important for the definition of the management strategies of a CXP plant. And in order, in this way, it is possible to know also the time available for a complete drainage of the solar plant in emergency condition. Let's start with the melting test. Okay, we start. Okay, we start heating all the system until we reach the temperature of 270 degrees. The output voltage applied by the electric supplier is equal to 4.5 volts. Here we can see the trend of the temperature. Inside in the middle section of the two receiver, and in the color welded between the two receivers. All the process take about 5.5 hours. We can see that the process starts at a temperature equal to 221 degrees and finish more or less here at a temperature of about 250 degrees. If you want to see in detail the different section of the receiver, we can see that at the center section, we can see that the process starts in different moments in one tube and in the other tube. More or less, we have a delay of about 30 minutes, and this is depend on the configuration of the two receiver. We suppose to the inclination of the line. Then it's possible to note that the thermocouple positioned in the upper part of the section start higher, before to melt. In fact, the thermocouple measure a higher temperature than the thermocouple positioned in the bottom part of the section. And moreover, we can see that at the beginning we have a slow, the temperature rise very slow between the 220 degrees and 230 degrees. After this temperature, we have a sudden increase in the value of the temperature. And it is due to the fact that the salt is mostly part is liquid, and so facilitate the melting process of the remaining part of the remaining solid part. Instead, in the central collar, in the collar welded between the two receivers, we can see that the melting process starts after that the salt is melting inside the receiver, and this is due to the fact that in this section the heat losses are very high because they are the support of the pipes. So the heat losses increased. The temperature rises very slow at the beginning of the process until suddenly we start with the melting process go very, very fast. In fact, it's not clearly visible the melting process, and this is due also in this case to the fact that the salt in the two receivers are liquid, and so accelerate the melting of the salt inside the central collar. Instead of here we have done the freezing test. Okay, for the freezing test, these tests were carried out under the same real condition as said before, in order to simulate the work condition that can occur in a real plant. So during the night circulation and in emergency condition with the pump blocked. So we start, we heat all the system until 270 degrees. We maintain the system at this temperature, at this stationary temperature for 1 hour, and then we turn off the jaw heating system. So the temperature began to decrease until the salt started to freezing. Here we can see that the area that cools first coincide also in this case with the color welded between the two receivers, and the whole time necessary to complete the process is about 3.5 hours. So it's faster than the melting process. In detail, we can see that here are the temperature of the thermocouple position in the central section of the receiver. In this case, the two receivers start the phase change more or less simultaneously, and go more or less at the equal trend. Also, in this case, you can see that the solidification starts on the external walls, that is the coolest part, and then proceed towards the inside of the tube. In this picture, there is that the trend of the temperature on the central collector. The process in this section is faster. In fact, is ending just over 1 hour because of the higher heating loss. So, as a result of this test, we can say that in order to melting the salt inside the receiver tube, we have to supply a power of 6.26 kilo. And the whole process takes about 5.5 years. Instead, concerning the freezing, the salt inside the two receivers takes about 2.5 hours to solidify without salt circulating. And with this test indicates that the beginning of the phase change, both phase change, so melting or freezing, occurs at the coldest points and continue radially from the external surface towards the inside of the tube. Okay, the last test that we have done at the facility in Enea are the evaluation of the receiver heat loss. In Casaccio, we have realized another test bench dedicated to the evaluation of the heat loss in the receiver tube. This test bench is different from the other test bench used in other laboratory because also in this case we use the Joule effect to weak the receiver. In fact, we can see here the two clamps where is connected the electric generator. The electric generator is the same used for the melting and freezing test. So the control logic is more or less the same of the other test bench. In fact, also in this case, we have the software developed in LabVIEW that we use to regulate the electric power for the acquisition of the data. The voltage of the electric heater is regulated as a function of the maximum temperature of the steel tube measured in the middle section of the tube. This tube is have more or less 23 thermocouple installed in order to have to monitor with accuracy all the temperature profile. So we have 12 thermocouple inside the steel tube, and another 11 on the external surface of the glass tube. The thermocouple positioned inside the tube are in direct contact with the internal surface of the steel tube. Here we can see the two clamps, one and one here. The two clamps are mounted on a little pipe welding to the two ends of the tube. This little pipe was insulated, and we have to pay attention that here there is the bellow, and we have to control that the temperature of the bellow doesn't rise up very up, because otherwise it could damage. Also in this case, the main objective of this test is the measurement of the heat loss, and with the heat loss, the evaluation also of the emittance of the cooking. The procedure, the test procedure is to heat the steel tube directly by the electric generator. We have performed the test in the range of temperature between 300 degrees to 550 degrees, with a step of 50 degrees. And for each temperature, we have performed 3 tests. The heat loss are evaluated measuring the electric power required to maintain at the steady state the steel tube. Here we can see an example of the temperature distribution measured along the steel tube. We can note that the temperature is constant in an interval of 1.5 meter from the middle section. So we can express the heat loss per unit length of the receiver with this equation in function of voltage and the current supplied by the electric generator. To evaluate the accuracy of the measurement, we have evaluated also the standard deviation for all the 18 tests that we have performed, and with this equation for the voltage, the current, and then also for the temperature of the steel. We have seen that in the central section of the tube receiver, we have positioned 3 thermocouples spaced of 120 degrees each other. And we can say that the temperature is quite uniform on this section. So we can consider the mean value of the temperature in the center of the receiver as the average value of the 3 temperatures measured. And then we can evaluate the standard deviation of the average steel temperature in the central section with this equation. Here I reported a summary of the results that we have obtained in one of our tests on on one receiver. And also the other reported also the standard deviation for the voltage, the heat loss, and also for the temperature, the still temperature. But we can see that the standard deviation is very, very small, in the order of 0.1%. So we can say that the measurements are very accurate. The system of measurement is very accurate. Okay, here are represented the heat loss as a function of the average temperature measured in the middle section of the steel tube here. But in literature, normally it is used this fitting model that expressed the heat loss in function of the difference between the temperature of the steel tube and the ambient temperature. So we have evaluated the A and B that are two constants evaluated by the experimental data, and we have expressed the heat loss in function of the difference in the temperature between the two temperatures. After that, as said before, we have also evaluated the dynamic transfer of the coating of the receiver because we know that the thermal power is exchanged by radiation can be expressed with this equation where epsilon s is the dynamic transfer of the steel tube. And so we can, because the thermal power exchanged by radiation is equal to the heat loss. And so in this way, we can evaluate the dynamics of the coating. Here is the trend of the dynamics of this, the tube that we have tested. Okay, thank you.
Yeah, thank you, Valeria. More questions? For me, the topic about receiver testing is very interesting because we're doing it here also in the Quartz Center, as you know, with Johannes.
But then I have to meet to Johannes. Yeah.
We do differently, as you know.
Yes, we have the different test bench. Yeah.
Other questions?
I have a question about the heat tracing. Did I understand it right that you have one heat tracing circuit and you have always more than one temperature measurement, like 6 or something like this? I saw.
Yes, we have many temperature measurement because the circuit of the PCS is a long circuit.
Yes.
And every pipe, let's say level pipe, have one or more cable. So for each pipe we have more than one thermocouple in order to control especially the critical point.
Yeah. I mean, for the Joule heat, I'm not so much interested for the Joule heating, but for the ones mineral insulated heated ones, how do you deal with this for the normal mineral insulated heating segment? Not the receiver tubes, but the other.
No, the other
parts
of the circuit.
So if you have a single heating circuit, you install one or several?
No, several.
Okay.
Yeah, several.
And what is your strategy when you control it? So you have 6 different temperatures. Which one you use?
We have 6 different temperatures and a temperature for at least one temperature for every cable. And when there is a critical point, such as the curve or a valve,
the lowest temperature for controlling.
we control the lowest temperature of the whole temperature related to the cable.
And the temperature level you mentioned, you use 250 or 300 degrees. Why don't you go a bit higher?
Because the melting temperature is the melting range of temperature is between 221 and 240, and so because The thermocouple is outside the pipe, and also the salt that comes from the tank is at the higher temperature, is around 40 degrees, 400 degrees, and so we are quite sure that during the flow of the salt, also if the temperature of the pipe is near the melting temperature, it doesn't affect the flow of the salt.
Okay.
Because the salt is moving, so
Yeah, but you preheat to 350 or 300 degrees, but your salt has 400 degrees. So my question was, why don't you go higher for
okay, the salt can go out from 300 to 4. It depends from the test that we want to perform in these days. So it's variable, the temperature that we flow the molten salt.
Okay.
Obviously, if we have to do a test at 450, normally we preheat all the circuit at 300 degrees in order not to have a shock temperature on the piping, in order to have a more similar temperature between the salt and the metals. It depends on the test.
Consortium.
I have a question regarding the melting test. You use the Joule heating system to melt the salt, but did you have additionally heats of like the sunlight itself, or were the receiver shaded?
No, only the Joule effect because the test bench is inside a technological hall, so we can simulate the sun radiation.
I also have an additional follow-up question. So I calculated you use 6 kilowatt for the melting of the frozen, and it was, I thought it was 4 meter, maybe or 5 meter long.
And the two receivers are 4.5 meters long.
So it's about 1,500 watt per meter. That's a lot. So I assume that's not really necessary, such a high power. From what we saw, because then we have trace heating and pipes, that's far lower. So you don't need all the power, I would assume, or that's oversized a bit, the power for the test.
Power is the power needed to maintain to reach the temperature of 250 degrees, at which at this temperature the salt is all melting.
But that's the installed power. It's not the power you use for melting. So it's switched on and off.
No, it's the power measured at the two hands of the receiver tube, not the power supplied by electric generator. So we are subtracting all the power dispersed along the line, along the cable. Okay.
Yeah, more questions? Thank you again, Valeria.
Thank you.
Interesting. So, Dominique, Paula, I understand that you continue presenting, and are you clicking the slides yourself, Paula?
Yes, I will be doing the presentation through my computer. Okay, so maybe I can already start to share my screen. I believe you can already see. Just give me a moment.
Yes, we can see.
Okay, great. Just give me a moment. Okay, so I think we can start. I believe you can hear me well, right? Okay, great. So good afternoon, everyone. My name is Paula Martins. Some of you already know me. I will be doing this presentation to close this session of procedures on melting and freezing. Actually, this presentation should be done by my colleague Radia Telkadi. Unfortunately, she's a bit sick and she could not join during this afternoon. Hopefully, she is recovering. And in any case, I will try to do my best. So this presentation is divided more or less into 3 different sections. So first one, I will be explaining to you how do we proceed in our platform in melting and freezing operations. Following up that, I will be also explaining a bit about NOx emissions, foaming and salt handling. And to end this presentation, I will be briefly talking about shift operation in our facility. So starting by a small introduction for those who don't know our facility. Some of you already do, of course, but for those who don't, I will briefly explain to you. So this drone picture presents to you the Evora Molten Salt platform. This is a research infrastructure that belongs to Renewable Energies Share of the University of Evora, and in it we implement projects that intend to validate the use of molten salts, both as heat transfer fluid and also as a storage medium. So in this presentation, I will be more focusing on HPS2 loop, which is this loop here. If you can see my screen, my cursor, this loop here that is built up with 3 big systems. First, the thermal energy storage part, which is built up with 2 storage tanks. This is the cold and this is the hot tank. So it's from this tank that we pump the salts to the solar field, which is the second big system that we have. It's a solar field with around 680 meters, composed with 4 solar collector assemblies. This is a patented collector by TSK Flagsol, which was one of our partners in a former project, which have the same name of this loop. So the project that built up this loop was HPS2 project that brought together a consortium of companies and also University of Evora and DLR to build and then to operate this facility with a ternary mixture of molten salts. So this is just a small introduction for those who does not know our facility. In this slide, you can see our P&ID. I will not be bothering you with small details, but I think it's more or less easy also to read the picture. So these 2 circles corresponds to the storage part. So cold tank, hot tank, as I explained in the previous slide. So we pump the salts through this solar field, and then in normal operation, we would go to hot tank and then also to the steam generation part. Just a brief note, I will not be discussing normal operation procedures here in this session. Nevertheless, our steam generator actually is not working nowadays, so this part is not really active. And what is exactly shown in this picture, it's the startup sequence. So in the beginning, we pump the salts through the solar field, and then we use the bypass line directly again to the cold tank. We do this just for the sake of preheating all the pipes before really start normal operation. Besides that, also during night operation, we also use this path in order to keep all of our pipes warm and avoid have to preheat all the piping in the next morning. Okay, so closing now this introduction part, I will now be discussing melting and freezing operations at our infrastructure. I would like just to mention that this HPS loop already had 2 different test campaigns, one with a ternary mixture of molten salts supplied by one of our partners, which is Yara, and another one using normal commercial solar salts. These pictures more or less illustrate the procedure, let's say. So for the Yara salts, we used this machine that you can see on the left picture. So this is what we call a pre-melting unit, okay? So these pre-melting units have three different steps, let's say. In the first step, the operator will be putting the bags of salts inside this part, which is a crusher. Then this conveyor belt will move and transfer the salts to this conic tank, and it is in this conic tank that it's traced and insulated that we execute the pre-melt of these salts, and then later when they reach the temperature desired, we transfer them directly to our drainage tank. This was the procedure for the Yara salts. Actually, for the solar salts was not the same. For the solar salts, we directly used the melting unit installed in our drainage tank because the facility was foreseen to do this melting of the salts inside one of our tanks. Okay, so this is also pictures of the procedure. So this first picture more in the center, you can see here the operators, the bags, so they would be doing this by batches. So at the time we had 2 shifts to execute this salt melting. Here it was already during the salt melting, this foam, it's not exactly steam as it is mentioned here, but this foam is due to the boiling of the crystal water that these salts have in its composition. So part of the process of the melting process also includes this boiling of the crystal water, and this is what you can see here on this picture on the right. Passing now to freezing operations. So okay, first we melted, we executed the test campaign of HPS2. I will be well, saying here some storytell for you to understand. And then when we finalized HPS2, we already had another follow-up project, which is called MS Opera. But MS Opera wanted to test a binary mixture of molten salt. So in the end, we needed to really not only freeze the salts, remove them from the loop and from the storage tanks, clean everything for them, for then follow up with the melting of the new salts. So this freezing operation, it's included in these handling procedures. And at the time with the Yara, what we did was first to drain the hot conveyor.
Paula, we can't hear you anymore. What about the others? Paula?
Maybe to ask Dominic, is it working for you?
Yeah, Dominic is
Here,
Paula.
it seems to be
Paula
on.
disappeared.
I'm trying to reach Paula by mobile.
Hi, Paula. So from our point of view, you can start.
Okay, can you hear me and can you see my presentation?
Excellent.
Okay, I'm very sorry for before. We had a problem with the internet connection, but I think now I can conclude and resume this presentation. I will just maybe go back just one slide before. So because I'm not sure exactly when did you lost me. So I finalized more or less in this part. So this is pictures of the melting process that we did. Solar salt with
Paula, the connection is bad again.
good. I hope that I can.
Now we can hear you. Perhaps you just switch off the video in case it's a bandwidth problem. No, we don't hear you. You're frozen. We need a melting process. No.
Can you hear me?
Yeah. Always 3 seconds and it's gone.
something, right?
I suggest, Thomas, would you be prepared to switch with Paula?
I think the last talk is from.
Isn't it yours? Ah, no, Pedro. Pedro, I'm sorry. Sorry. Yeah.
Yes, actually, I would suggest this presentation could be shifted for tomorrow morning.
Yeah.
It's not worth it.
Paula, I don't know if you can hear you, Dominique. The suggestion from our side would be to continue with Pedro's presentation.
Yes,
And,
Paula is suggesting if, yeah, so Paula is suggesting if Pedro wants to finish her presentation.
Pedro finished Paula's presentation.
No, I'll rather Paula or Rabi having the presentation tomorrow.
Okay. Okay, I'll tell her.
Otherwise, it's the minus of gender equality, isn't it?
No, because Paula is the one knowledgeable. Paula and Rabi about the presentation.
Okay, so I have to see now. What is my... Pedro, that is probably that one from yesterday afternoon, I suppose. Yeah, sharing the screen. Where's my screen share? Share the screen, share the screen. Share the screen. It's good. Okay, I hope you can hear us. Dominic, can you confirm?
Now it should be
Now
working.
Dominic is on the phone. Paula is on the phone. We see Paula. Paula is online.
Well, good afternoon to you all. So I guess the best is that we skip the presentation we were having for tomorrow. And the objective of this last presentation was to give you an overview of what we have been seeing here today, mostly with the larger size installations that have been presented by DLR, by ENEA, and by the University of Évora. As we just started, we will have the rest of the presentation tomorrow. I take the chance to present myself. For those who do not know me, my name is Pedro Horta. I am the head of the Renewable Energies chair at University of Évora and also the coordinator of SALTOpower. So SALTOpower gathers these three institutions, DLR, ENEA, and University of Évora, around research topics concerning the use of molten salts in energy system applications. One of the objectives of the project is exactly to empower researchers, young researchers, in developing their careers around these topics. And of course, we see also the opportunity to have a joint venture on the development and use of our research infrastructures at DLR, ENEA, and University of Évora, which together have some of the most important research facilities in Europe in this topic. So to give you an overview of these facilities, the order in here is purely alphabetical, but actually we should start with the facilities at ENEA, which actually deployed this line of research at this larger scale with the starting of operation of the PCS and MOSE infrastructures in 2002 and 2003. So as we have seen already, MOSE enables testing of components for molten salt operation, whereas PCS already had a line of a parabolic trough circulating molten salts, which was innovative at the time and deployed this line of research and this technological possibility. We had then in 2019, in January 2019, the starting of operation of the thesis facility, both thesis store and thesis home, as has been presented, focusing on large-scale thermal storage, but also on the testing of molten salt components. And we have had very impressive examples of the use of this infrastructure in these experimental tests. And finally, in the end of 2021, we had the inauguration of Evora EMSP, Evora Molten Salt Platform, with the HPS2 loop inauguration, which stands as the largest full-fledged research facility, including both the thermal storage and solar field components. And later, we will have the commissioning of yet another molten salt loop, which is connected to a thermocline molten salt storage, but the commissioning of this infrastructure is due only next year. So the existence of these facilities are definitely an instrument for researchers, but also for industry, for the development of new components, for the development of new technologies, and definitely for the development of new maintenance and operation procedures. And so, looking into the purpose of these different facilities, what we can see on the size of thesis is that thesis store is focused on the development of the thermocline concepts with molten salts and filler materials, as we have been seeing here. So it has a devoted infrastructure for already large scale storage systems. So definitely a pilot scale, which is representative of what would be the operation on a real scale system. On the other side, we have ThesisCom, where we can test process technology developments and do the qualification of components for molten salt operation. So with PCS, which was the first infrastructure, we would already have the testing of the connection between solar fields and thermal storage system using molten salts as both heat transfer and heat storage media. And in MOSE, we can perform tests again on components, looking, for instance, into corrosion under different molten salt mixtures. The aim of the HPS2 projects was the demonstration at a larger scale of what would be a CSP plant, relying only on the use of molten salts. And this facility enabled not only this demonstration that it is feasible, but also is enabling now the testing of different plant components, but very important, of different operation and maintenance strategies. And this is definitely of a very high value for the CSP industry. It is important to mention that though this infrastructure looks into what would be a CSP plant, it also regards the thermal storage component as a component on its own, as we can see also in the thesis facility, because definitely our vision, and I believe it's our common vision, is that the thermal storage component might also and will also play a very important role in the energy system, besides the topic of CSP. So CSP is one of the possible technologies which will be charging this thermal storage component, but not necessarily the only. With the loop for new sol at EMSP, we aim also at demonstrating a thermocline concept, possibly with filler materials. Actually, the storage as a filler material already installed. We will be able to change these filling materials, but also to use different molten salt mixture, which is also one of the research topics we are able to develop. In terms of the scale of these facilities, we are talking already about dozens of tons of salt. So starting with PCS, which has 12 tons salt mass. So based on solar salts, the use of solar salt binary mixtures on MOSE 1 ton. We then go to thesis, already going to dozens of tons, so 85 tons of binary mixture, and the thesis COM facility 25 tons. And finally, on HPS2, we have the possibility, and we have already tried 2 different salt mixtures, binary and ternary mixture, 72 tons or 92 tons respectively. And in new salt, we will be able to use 58 tons of a ternary mixture. Regarding the temperature range, of course, it's related with the salt mixtures used. So all of these structures, except for new salt, are using solar salts. So the temperature ranging between 290 and 560. At HPS2, we can go a bit further to 585 degrees with solar salts. Both infrastructures in Évora can also use a ternary mixture. This is also the case of MOSE and thesis COM. Thesis Store can also use other mixtures, though I'm not sure you have already used other mixtures in this facility. So on HPS2, we did use already both salt mixtures. So there is already an experience gathered also with the interchangeable salt mixtures. In terms of thermal capacity, PCS already had reasonable capacity, 400 kilowatts thermal, kilowatt hour thermal, but both thesis and EMSP facilities are already multi-megawatt hour facilities. So definitely we are already working at the scale which is relevant for industry and which is representative of what would be real scale plants. And finally, looking into the salt handling procedure, so there is a lot of experience already gathered in these different infrastructures. In all of them, we can see the use of tanks with electrical heating to melt the salts. In the case of EMSP, we have also used a dedicated movable pre-melting unit. So there's also this experience. As I was mentioning, in the case of EMSP, we have had this experience with 2 different salt mixtures, binary mixture and a ternary mixture. And finally, regarding the emptying of the salt plants, which is not the same as the disposal of salts. So the disposal of the salts is a topic where experience is still required. But emptying the plant itself, it's an issue. In the case of thesis, this is a question which has not yet been defined. The process is yet to be decided. In the case of PCS, this operation has never been performed, but likely they will be using the same strategy as they use in MOSE, which is a much smaller system, of course, which is basically to remove the salts to a container and let it freeze and then pack it. In the case of HPS2, we have used already 2 different methods that Paula was just showing. What the first one, which was the solidification using a cooling belt. This was a process which was suitable, though demanding, both in terms of efforts and of financial resources. So we are not sure this would be a process used in a large-scale plant. It was a resource we could find at the time because we really had to empty the plants. But more recently, and we will see a presentation about that tomorrow by Nicholas, we have tested a different process, salt dilution, which we believe it's a promising alternative for this kind of operation. In the case of new salt, the system has not yet been commissioned, and so we will be deciding what will be the procedure. But definitely on HPS2, we could already gather some experience on how to empty these plants whenever we need, or a salt mixture exchange or any maintenance procedure. And this pretty much completes this overview and comparison of this infrastructure. So we thought it would be important to provide this summarized information, not only for the researchers present at the Fast Track School, but also, and I would say most importantly, for potential industrial partners, because these facilities, of course, are there to provide services and the ability to develop new technologies, new components, and new strategies for the operation of it. Thank you so much. I'm open to your questions now. No, I don't think there are.
I was thinking about starting here a short presentation of other participants who are also dealing with hardware or things.
Sure. Sure.
To know each other a bit. We have some time left.
Yeah, sure. We have a lot of time left.
I mean, some people were able to talk here in the front, but others in the room also have experience, also have hands-on experience. I would suggest to know each other a bit before we go then to Elshof together. And perhaps go through the rows, and each of you present yourself shortly, what you're doing, what you might want to contribute or get as experience from here, just if you want to. Perhaps we go through the rows. Christian has started, Thomas has presented. Oliver. Would you like to?
Sure, absolutely. Hi, everyone. So I'm working in Imperial College's campus in West London, in White City. We're a small company called Aid Energy, and we're developing a molten salt based phase change energy storage product. And so wanted to come here and just make new connections and learn a little more about the activities that are going on through this program.
And are you coming to Elshof with us in an hour or so?
Sorry, no. I have to depart.
He will be only here today, so last chance to.
Yeah, but this is also the point. Yeah. Okay, but
is there something you'd like to share about your experience, and how do you see your experience reflected here on the different experiences we have been presented?
I think I'd like to weigh that up and come up with a real answer.
Sure.
Yeah.
Okay. Anna Chiara, we had you.
Morning, I'm Raffaele Di from EMEA, that I've been working since 2003 in this company in activities related to the concentrated solar power, thermal energy storage, hydrogen production by thermochemical cycle, and also economical assessment. Tomorrow I'll present a small presentation about the MATS facilities that concerns the thermal energy storage by molten salt built in the Egypt and coupled with a solar field and a desalination plant. And so I have experience in the molten salt storage, also in some prototype related with the phase change material and also at medium and high temperature. Right.
Okay, and will we meet you at ELSOF later on?
Yes.
Okay. Giuseppe, we had you already. I think so. Do you want to continue? Yeah.
Hi, I'm Barbara. I work at DMO in the Netherlands, and I'm working with molten salt, mainly on industrial applications. So I teach how to fluid and thermal energy storage. And yeah, come here maybe to learn a little bit more about molten salt from people that work with it on a daily basis. So we can transfer some of the knowledge to the application that we are investigating. Yeah. My background is on chemical engineering, so we're doing this mainly on chemical processes. And yeah, not usually yeah.
Okay, thanks, Deborah. And will you be at ELSOF with us?
I don't think I will be able to.
No?
No.
Are you around tomorrow as well? Or
Yeah,
you-
I am.
Okay, Niklas, you have something to tell.
Yes, Niklas. I'm working in DLR since 5 years now. Only in the topics around molten salt, mainly regarding the Ibra molten salt platform. So I started here in DLR when HPS2 was running. Then we did the commissioning together in Portugal for 5 months. I was there for doing commissioning and then also testing. At the moment, the MSOPRA project is ongoing, which Pedro already mentioned before. I'm the project coordinator of that project. Yeah, tomorrow I will also have a presentation about the salt dilution process, which we now did already twice on the MSP, once with the Yaramos, once with solar salt now a few weeks ago. Yes. So I'm mainly involved in all topics from project acquisition to testing on site. Yes. So I already have some practical experience. I was in Portugal on the facility for roughly 1 year in the last 3 years. Yeah, I did several tests on site.
Yeah, thanks, Niklas. Are you going to be at ELSOF with us?
No, but I will be here tomorrow.
Okay.
Yeah, to be honest, I did not know that we would go today to the ELSOF, so I was really impressed.
I mean, we will go right after that meeting.
You know.
Okay.
But I have other appointments, yeah, and
Bring her along.
it will be a huge amount of people. You want to invite them? Okay.
Gary.
So I'm Gary. While I have about 30 years of experience in CSP and collectors, including parabolic charts, my experience in molten salt is very, very limited. So I had a bit of experience ages ago operating a molten salt receiver in Spain. So I encountered unplanned freezing events, and I know about trace heating that doesn't work as planned. But I would consider myself a complete rookie. So, but about 1.5 years ago, I joined GlassPoint, and my colleague Klaus Jürgen, who is much more familiar with molten salt than I am, so we inherited some knowledge, hardware, information about molten salt systems, because GlassPoint colleagues in the US, they already designed, built, and operated a small molten salt parabolic shaft system in Oklahoma. But my target, as I said, I'm a rookie, is to absorb as much as possible and refresh some old and get some new connections to make our next step, which will be kind of a pilot or prototype. Not maybe the immediate success, but at least have a good start with that. So that's my side. And I will join later on.
Thanks. Nice to hear. Matteo.
Yes, I'm Matteo. I am a PhD student of University of Vergata in collaboration with ENEA. and I am an energetic engineer. So this field, I have experience in this field, especially theoretically, not practically, but my PhD person is about the production of hydrogen through perovskite with combined with
Mit diesem Computer.
Okay.
Okay, so easy. So then I stop sharing, yeah, and I think that now Paula shares, yeah, again. We have a lot of presentations from Paula. I moved the speaker a bit that we can hear. So we see the screen, Paula.
You can hear me
It's,
and see the
we can hear
presentation,
you.
right?
We see the presentation and can hear you, yes.
Okay, great.
We continue now with a presentation about the EMSP facility with control and monitoring.
Okay, thank you very much. So as Thomas said, I will be presenting the MSP facility. I briefly already explained a bit in the presentation before, and I will also be presenting to you how we control and monitor our facility. This will be kind of a short presentation, so don't worry, in 10 minutes you will be in the coffee break, okay? Or if you have any further questions, of course, we can extend. So as an introduction, and here maybe I will detail a bit more than in the presentation. In the bottom on your right side, this is what we call HPS2 loop. This is installed at Ever Molten Salt platform. Ever Molten Salt platform belongs to University of Ever and is being managed by Renewable Energies Share Group and also managed by DLR. So this platform started with this loop under the scope of a project called HPS2 loop, and also we still call it HPS2 project, sorry, and we still call it HPS2 loop. So this loop, as I already explained, is made of three main systems, which is our steam generator, our storage tank, and our solar field. So for the solar field, is a solar field of around 680 meters long, a heliotrope collector, is a collector patented by DSK Flaxol. We can reach up to 560 degrees Celsius in this solar field. Of course, this outlet temperature, it will depend on the mixture of salts that you are using. With Yara, the maximum would be around 500 degrees. With this solar salt, will be something around 565. For the tanks storage system, this is made through two tanks systems, so one cold and one hot tank, with a capacity of 5.4 megawatts for our thermal. Then we also have the steam generator with a total power of 1.8 megawatts thermal, a maximum pressure of 140 bars, and a maximum temperature of around 560 degrees. Nowadays, yeah.
Okay, that's more technical.
Any problem?
Everything is fine now, Paula. We had the wrong screen here.
Okay.
We can hear you. We can see the EMSP.
Okay, yeah, I will continue. I'm sorry if I did something wrong. Well, at least you look to be laughing. Okay, so these are the three main systems that we have in the HPS2 loop. Besides HPS2 loop, we also have NewSol loop, which is, I will not be focusing on this loop because It's not yet operational. We did not yet commission it, but we have a thermofine tank which is being connected to a Fresnel solar field, and also in the future it will be connected to organic engine cycle. But as I said, we are not yet operating it, so this presentation will be more focusing in HPS2 loop. Passing now to this slide. Here it's presented the, well, this is the P and IV, but it's in highlighting in these three different pictures the different operational modes. One of which I already mentioned in the presentation before, so it's path for the startup heat. So we go from the cold tank through the solar field and again to the cold tank. This serves mainly the purpose of preheating these pipes. It's also being used during a night operation. We also have the normal operation, which will be from the cold tank, passing through the solar field, and then filling the hot tank. If we had if we had our steam generation system operational after the hot tank, we would be filling also the steam generation part and then coming back to the cold tank. As that is not the case, whenever we have the hot tank full, we just transfer the salts to the cold tank. So passing now to the control and monitoring and presenting what we have on site, let's say. We have three different interfaces, let's say. One to control the loop, the storage tanks and the process itself. Another one to control the solar field, and one last one still to control the heating systems. Of course, we have interfaces mainly between the control of the solar field and the control of the hydraulic loop. So we use a software of Siemens, the Siemens T3000 for the DCS, and then we also have the FSC for the interface of the solar field. Passing now to this slide, this is snapshots of what we can see. Of course, we can see more than this, but this is a general overview of the plant. Also, you can then inside the DCS also see details of each one of the tanks, also from the steam generation system. This is also only explaining the general overview of the plant. And in the picture on the right side, what you can see is the 4 different SCAs, so solar collector assemblies, in the middle. And on the right, you have the meteorological parameters and also the list of alarms that you can have on your plant. So it's through this software that the team knows if we have any problem and adjust operations accordingly. And also here parameters related also to temperatures that I can. So continuing, as I already mentioned, we already tested 2 different salts. And due to that, of course, then we also adjust the limits because the operational parameters of the salts are not the same in which regards to temperature. So here it's a table of what we have in solar salt and the other most molten salts are the parameters that are included in the system. And of course, the control system is programmed the temperatures with limits and set points depending on the salts that we are using. Okay, passing now to sensors and monitoring. So obviously to control the process, we are mainly controlling here temperatures, pressure, and flow. So in the cold line, for example, we had 2 flow meters, 1 vortex, and another one ultrasonic flow meter. And then we have several temperature sensors, either in the piping, also in the solar field. And also we have pressure sensors. So we have capabilities of real-time data acquisition, data logging and storage, and we have integration with this the controllable elements, of course, and the idea is to regulate either the flow and the pressure in the solar field. and to ensure system safety and efficiency. So for this, mainly we have automated control systems. We have only slight manual operations. Mainly is everything done from the DCS and not from manual operations. Data storage as well. So what we collect, or what we are able to collect, is the meteor station and all the operational data, temperature, pressure, and flow rates. Besides this, and also a very important aspect for us, is also the control of the electrical consumption data, and it's according to this that we also adjust and optimize our operations. And this is it. I think I am ahead of time. Thank you very much for your attention. And if you have any questions, just let me know.
Could be there sometimes. Thanks a lot, Paula.
I could not hear you well, actually.
Can you hear us?
Kind of. I can hear you, but not so well.
Okay, then I maybe repeat the question if there are some from the audience. So, any questions from participants? Online questions? Maybe I have a question. Do you show two control systems? One was for the optical part, one was for the remaining, the molten salt part. Is there an interlink of the two systems, or
Yes,
is the operator the interlink?
They are interlinked, yes. But to do the control of the solar field, they really need to operate through the FSC.
So, but is there exchange of data between the two systems?
Yeah.
Okay. Any other question? Maybe was also hard. I hope you could understand more or less. Okay. The audio quality was not so good. So I think we make a coffee break now. I suggest to start again at 10:45. Then we have a coffee break now. Okay.
And there are 3 people waiting again.
Yeah, okay.
Waiting for the coffee break.
Yesterday Dominic did it, but Dominic is not available today, so that's our.
Do you need any help, Thomas?
So the recording, I switched the recording off now, yeah.